Thank you, Zach, and good morning. My name is Evan Kawabata, and I'll be presenting my thesis titled Concept Design Tool, Automation of EPLA and One-Line Diagram Generation. Before I begin, I would like to thank my advisor, Professor Martin, for his invaluable assistance and guidance throughout this project. I would like to thank my reader, Professor Boyd, and my editor, Professor Harris, for their feedback on my thesis submittals. I would also like to acknowledge the Staten Island Ferry for use of their EPLAs and other drawings. The objective of my thesis is to develop a tool that will simplify the analysis of the electrical distribution system of a ship at the concept design stage. This is important because EPLAs typically begin as blank documents or copied from similar vessels. If a method can be developed that allows designers to quickly and easily estimate a vessel's electrical load, then more design iterations can be evaluated. The focus of my thesis is on automating the generation of an electric plant load analysis with minimal input from the user. For this presentation, I will go over the background and theory before discussing the methodology behind my EPLA generation tool. I will then discuss results, conclusions, and make recommendations for future work. The concept design stage is the earliest stage in the design spiral. In this stage, the smallest amount of information is known about the vessel. Since electrical analysis typically occurs much later in the design spiral, developing a quick estimate early in the process allows designers to consider it much sooner. Concept design typically has a lot of variability as major design decisions have not yet been finalized. This means that many different designs are iterated before one is selected for further development in preliminary design. So what is an electric plant load analysis, or EPLA? An EPLA is one of the first and most important documents for electrical analysis. EPLAs are a collection of the electrical loads of a vessel and the expected operating conditions for generator sizing and one-line diagram drafting. Because equipment isn't always running, EPLAs make use of something called a load factor. The figure on the right displays an example load throughout the day. Hours of the day are on the x-axis, and load in megawatt is on the y-axis. And this shows that there is great variability throughout the day. If a generator is sized at the maximum load of 6 megawatts, then it would be oversized. However, if a generator was sized at the minimum of 1 megawatt, it would be dangerously undersized. Load factors are compromised and use a statistical average to best approximate the appropriately sized generator. Load factors differ depending on the vessel's operating condition, and some example operating conditions are the cruising, shore, or emergency condition. Above me is an example EPLA for the ferry MV Delaware. Going left to right across the EPLA, first is a numbering system for the items, followed by an item description and quantity. Next is a rated kilowatts for each unit and the total connected kilowatts. Finally, the load factors and the operating condition. In this example, the EPLA considers normal operation at sea in the winter and summer. The effective kilowatt is in the load factors multiplied by the total connected kilowatts in use. How do one-line diagrams interact with EPLAs? EPLAs provide a list of the loads, while the one-line diagram illustrates the connection between the sources of power and the loads. Every one-line diagram has a power source, which is where electrical power is provided. This is typically through generators or shore power. Transmission is a transfer network consisting of cables and transformers. Distribution involves connection points for loads via switchboards or power panels. Loads are equipment that consumes electricity. EPLAs provide a list of loads, allowing us to work backwards in order to create a one-line diagram. In reality, one-line diagrams are much more complex, and here is an example one-line diagram for the all-class Staten Island Ferry. Here is the power source, which consists of 3 generators connected to the main distribution switchboard. The drawing then continues on to power panels and individual loads. The main guiding documents used were the DDS 310-1 and the NVIC 2-89. These documents provide recommended load factors for various ship operating conditions that were instrumental for this thesis. In 2019, Josiah Ng developed a script to automatically route and size cable based on a power panel input. The figure on the right shows his AutoCAD script connecting a load to a power panel. In 2021, Ben Hunt and Alex Kojal developed a design tool which used an EPLA to create a model one-line diagram and optimize generator selection. Their first goal is a primary inspiration for my thesis. For concept design, is there a way to automatically create an EPLA that can be plugged into their tool? The goals of the tool are to expand upon Hunt and Kojal's by providing a more realistic EPLA input. In keeping with a traditional EPLA, my tool needs to generate a list of loads, then estimate each load's kilowatt rating. Hunt and Kojal's tool also requires load locations to be identified, and this is not typical for an EPLA. To accomplish these goals within a year, I had to set some limitations. First, I had to choose a specific vessel type, and for this, I chose double-ended ferries. Next, I had to limit myself to ship service loads. This limitation reduces the number of items in the EPLA into something more manageable. Finally, I had to match the formatting input with Hunt and Kojel's program. Most importantly, their tool requires an item description, location, kilowatt rating, and load cases. My thesis focuses on double-ended ferries, but what are double-ended ferries? Double-ended ferries are ferries with two bows that can sail in both directions without rotating. The figure on the right is an example Molinari-class Staten Island ferry. Notice the identical structure on both sides of the vessel. For context, Staten Island ferry only operates double-ended ferries. In addition to normal ferry systems, double-ended ferries have two propulsion drives, which must be considered in the development of the EPLA. Most importantly, I have the most available information for double-ended ferries. This means EPLAs and other drawings to reference in the development of my tool. The goal of automation in the context of my design tool is to minimize user inputs to produce a reasonable output. This is achieved by using custom algorithms to estimate the kilowatt rating for each electrical load on the vessel. And this is ultimately in service of the main goal of estimating the total ship service power from the ship parameters. For my tool's programming language, I had to choose between Visual Basic for Applications, also known as VBA, or Python. VBA is useful because Microsoft Excel works as an integrated development environment, or IDE. This allows Excel to compile and debug code. From a user's perspective, interacting with a spreadsheet is extremely intuitive with Excel. This is important because EPLAs are giant spreadsheets, and Excel is the industry standard software for the creation and modification of EPLAs. VBA code can also interact with Excel features like spreadsheets, buttons, and macros. Python, on the other hand, was the language used by Hunt and Kojel. Python has many useful external packages for data manipulation. However, Python requires a separate IDE and the language itself to be installed on the user's computer. It is also harder to manually manipulate data within Python compared to Excel. With all this in mind, I decided to use Excel and VBA for my design tool. My EPLA generation tool is a custom Excel workbook with VBA code, and there are three primary worksheets that make up the EPLA. The first is the input worksheet, which is shown above. This is where the user enters vessel particulars and other inputs required by the program. VBA code is then executed using the buttons on the right. Here is a closer look of the inputs required by the program. The inputs include vessel particulars, number of decks, number of crew and passengers, design speed, total installed MCR, or the engine's maximum continuous rating, propulsion type, and ship type. The output worksheet is where the EPLA is generated. This worksheet begins as a blank table. After the EPLA has been created, this is the worksheet that is then exported as a CSV or comma-separated value file for use with Hunt and Kojel's program. In this sheet, the user can manually modify whatever they would like as in a normal Excel spreadsheet. Finally, the database worksheet is a list of all the loads that will be estimated by the EPLA generation tool. Here, the user can filter which items they want included in their EPLA. In addition, the designer can add custom entries to this worksheet that will then be copied into the final EPLA. The program begins by reading the user's input provided in the input worksheet. Then, the program filters all of the expected loads determined in the database worksheet. Together, these populate the output worksheet with a list of loads for the EPLA. I then use different algorithms in order to estimate the electrical load for each equipment. This then forms a fully fledged EPLA that the user is allowed to make whatever changes they would like. This EPLA is then exported for use with Hunt and Kojel's program. Everything in my program uses Excel and VBA. Everything in Hunt and Kojel's program uses Python. Diving deeper into the algorithms that populate the EPLA, the goal of the algorithms is to estimate the equipment kilowatt ratings in locations with minimal input. To do this, I must first consider the primary systems on the ship. Next, I determine which systems can be estimated by aggregation or an estimation of the total system kilowatt rating that can later be subdivided. Then I size individual components, independent of the system that they are a part of. And then finally, I consider constant and custom loads that are imported based on ship type. There are three types of algorithms used for estimating the kilowatt ratings. The first is the aggregate type algorithm, which estimates the total system load for a specific system, which is then distributed amongst different load locations. Examples of systems calculated this way are the lighting and HVAC, or heating, ventilation, and air conditioning systems. Next is the component type algorithm, where each load refers to a specific piece of equipment on the ship, which is then estimated from an EPLA regression. Examples of loads that use this algorithm are individual pumps and heaters. The constant type algorithm then captures loads that are already known or don't tend to vary with vessel dimensions. These loads are imported from the database worksheet. Some equipment that uses this algorithm is certain galley equipment or navigation equipment, as well as any custom loads that the user has provided. As an example, I will go over the HVAC system estimation, which uses an aggregate type algorithm. The total area is estimated to be length times beam times the number of decks. This is then multiplied by a conditioned area factor of 65% derived from an EPLA regression. This is then multiplied by an HVAC power density of 0.05 kilowatts per square meter taken from the HVAC rule of thumb guide. Next, the sensible heat gain for crew and passengers is considered, where the kilowatt rating is estimated to be the crew sensible heat gain times the number of crew plus the passenger sensible heat gain times the number of passengers, all divided by the SEER, or the seasonal energy efficiency rating. The SEER is a ratio of the heat output for a piece of equipment to the energy input. It's important to note that I use these values in my estimation. However, these values are very easy to change if the user wants to use different ones. The total system kilowatt is then divided by decks based on regression of EPLA. The system kilowatt estimation is split between upper decks, main deck, and machinery decks. Then, each deck is further subdivided by location nodes. The component type algorithm is a little different. Each individual load is estimated from its own EPLA regression. For simplicity, the MCR was used for equipment relating to the main engine, and displacement was used for all other remaining equipment. Using fire pumps as an example, the estimated kilowatt for a fire pump is estimated using this equation. The quantity of fire pumps is taken from the requirements outlined in Code of Federal Regulations, Title 46, Subchapter 76.10. After the kilowatt rating has been estimated, each load is also assigned to a location node. Well, what are location nodes? Location nodes is a system derived to assign locations with loads with locations along the vessel, and they are meant to mimic power panel placement on the vessel. I assume that there are 4 loads equally distributed along the vessel on centerline. The figure on the right shows roughly how nodes are spaced throughout the vessel. Each location node is a VBA object with name, longitudinal, transverse, and vertical position properties. The tool assigns each EPLA line item with a location node. Finally, how does my tool fit into the tool created by Hunt and Kojal? They require an EPLA input as a CSV file, which is the output of my tool. Notice the headings on their EPLA. Ship work breakdown structure, or SWIBIS number, which is a Navy numbering system, name, location data, power, voltage, power factor, and individual load cases. This example EPLA input then produces this cable diagram output. The program also performs generator sizing. Their tool again uses Python using the PyCharm IDE. They reference a separate software called GraphViz in order to produce the cable diagram visualizations. And here is a wonderful EPLA that my tool produced using the Olis class Staten Island Ferry vessel dimensions. Looking more closely at the emergency lighting, it matches the format of Hunt and Kojal's input EPLA. Note the SWIBIS number, name, and location data, as well as the power, voltage, power factor, and load cases. Load cases 1 through 5 are the anchor, shore, cruising, functionality, and emergency conditions outlined in guiding document DDS 310-1. Here is a comparison between the Olis class Staten Island Ferry EPLA and my tool's output using the same vessel dimensions. The idle, transit, and docking conditions are important to compare because they are the functional conditions of the vessel. For these conditions, the estimated ratings are quite similar, which is good. However, in general, my tool seems to underpredict. The big difference between the total connected kilowatt is because of large, unusual equipment that has a load factor of 0 in all conditions. This is the backup hydraulic pumps for the Voice Schneider drives. Accounting for these loads as custom equipment in the EPLA generation tool, my tool then has a similar value, but still underpredicts. The emergency condition also has a large discrepancy. This is because the Olis class EPLA includes additional emergency equipment, as well as they reference different load factors which have more weighting in the emergency condition. So in conclusion, I developed a tool which can generate an EPLA from vessel particulars with minimal input from the user. This tool is able to integrate with the tool created by Hunt and Kojal by estimating load kilowatt ratings and locations. Some challenges I encountered along the way was the limited EPLA availability. This harmed the accuracy of the regressions used for the algorithms. Also, the interactions between VBA and Python are clunky at best and must be performed manually and is not a very fun process. This tool has room for improvement, and I have some recommendations for future work. First, expand the functionality of the tool for more ship types. This would involve acquiring additional EPLAs for different vessel types. Next would be to improve the integration between this tool and other design tools. I know Excel recently gained functionality to use Python, so it may be possible to reference external Python functions or import their commands directly into Excel. Finally, since my EPLA has location and kilowatt data, there are additional electrical calculations that could be automated. Some that come to mind are power panel analyses based on location, voltage drop through cables, and a more detailed electrical model with feeders and mains. Thank you for listening to my presentation. Please hold any questions until after Kenna and Katie finish presenting their thesis.